Hey folks, my name's Nathan Johnston. Welcome to lecture 6 of vector calculus, which is all about the angular speed of a path. And so the idea in today's lecture is that we want to be able to quantify how curvy or how bendy a path is. And more specifically, we're thinking about like the particle on the path, not the underlying curve itself in this lecture. Okay, we'll talk about the curve itself and how bendy that is next class. For now, it's like, okay, how bendy is the path? Or maybe a better way of thinking about this is like, how quickly is the particle on the curve changing direction? That's what the angular speed of a path is. Okay. And sort of, yeah, intuitively, like what this is going to quantify is like, okay, like sort of how bendy the thing is. Okay. So, like, roughly speaking, we know what this means. Like something where you have to zig around a lot is going to be very bendy, and something where you don't have to zig around very much, it's a much more sort of gradual motion that's not very bendy. It's going to have a low angular speed. But like, how do we actually turn this into an actual mathematical definition? Like, what really are we measuring here? Okay. And the idea is what we're going to measure is we're going to say, okay, like the direction of the path that's encoded by the tangent line or the velocity vector, right? So what I'm going to do is I'm going to compute the velocity vector at one point in time, and then compute the velocity vector at another slightly later point in time. And then all I'm going to do is I'm going to ask, okay, how much did the angle between those two velocity vectors change? Okay. And sort of based on like, okay, so like we've got sort of an animation here based on images like this, like hopefully it seems fairly believable that if the curve is very, very bendy, then, what should happen is over even reasonably small time frames, the direction of that tangent vector, of that velocity vector, it can change quite a bit. Whereas if the path is quite straight, then that velocity vector, it's not going to change direction very much, okay, even over maybe slightly larger periods of time. Okay, so it's this angle between nearby velocity vectors that's going to serve as our quantification of how quickly the particle is changing direction, as our quantification of what we're going to call angular speed. Okay, so yeah, we're just going to measure that angle. We'll call that angle between those two nearby velocity vectors, we'll call that delta theta, and we're going to quantify how quickly does that change with time. Okay, so definition time. All right, so let's make this a little bit more formal. So suppose that you've got a differentiable path f, and we want to sort of quantify how quickly its angle is changing, how quickly it's changing direction. Then what we're going to do is we're going to let delta theta be the angle between the velocity vector at some time t and the velocity vector at some slightly later time t plus delta t. Okay, then the angular speed, we're defining it to be, well, what we call omega of t. This is the notation that we use for angular speed. And it's just the limit as delta t goes to 0 of the angle between the velocity vectors and, this change in time here. Okay, so in other words, it's like the instantaneous rate of change of that angle of the velocity vector. Okay, and I mean, for this reason, sometimes this angular speed quantity here, I'm calling it angular speed, but sometimes it's called the rotational rate of change or the angular rate of change, right? It's just how quickly is that angle between velocity vectors? How is the angle of the heading of the particle or the path? How quickly is that changing? That's what this is measuring. Okay, we would love to be able to actually compute this thing here. And this limit here, this definitional formula for it, is a bit of a nightmare to work with computationally. So let's come up with a formula that actually lets us compute it in practice. Okay, so that's sort of our goal in this video. But first, before we can get to that, we need a helper quantity, okay? And this helper quantity, it's going to be based on the observation that, okay, these velocity vectors that we're computing, like these velocity vectors that we're measuring the angle between, okay, the angle between them, it doesn't depend on how long they are. We can rescale them however we like. Okay, and we're still going to get the same angle between them. Okay, and as is often the case, if you only care about the direction of something or the angle between things, often the most convenient scaling is just scale it to have length 1. And that's exactly what we're going to do here, okay? So this is mild definition time. This isn't as beefy as the previous definition, so don't worry about it too much. Mild definition time, okay? We're going to introduce something called the unit tangent vector. And all it is, well, suppose that you've got some differentiable path, so you can take a derivative of it. You can compute the velocity vector, okay? And suppose furthermore that the velocity vector is not 0. Well, then what we're calling the unit tangent vector, all that is, well, it's the velocity vector divided by its length. So it's just the velocity vector rescaled to have length 1. Okay, the unit tangent vector is going to be really convenient for computing angular speed in a moment, but for now, let's just do a quick example to, make sure that we understand the definition. Okay, so let's compute the unit tangent vector for the path from R to R2 defined via this formula. And we've seen this one before. Okay, we saw this all the way back in lecture 1. Remember what this path here is doing is it's tracing out the unit circle except for the leftmost point. Okay, that point is excluded, the point -1, 0. Okay, and it sort of goes very slow at the left, goes very quick at the right, and then back to slow at the left. Okay, and we already computed the velocity vector of this. You just take the derivative of each entry and you get this velocity vector. And then the length of that, we already computed that a few lectures ago as well. Okay, the length of this vector here, after you square this first entry, square the second entry, sum them up, square root the whole thing, it simplifies down really nicely. And this is the length of the velocity vector. That's what we call the speed of that path. Okay, and now how do we compute the unit tangent vector? Well, just divide, okay? Velocity vector divided by speed, okay? This vector over here divided by this number over here, and what you get is, well, this here, right? I've just flipped this fraction because I'm dividing by it, so that's why it's flipped over here, and I just compute that thing, okay? And simplify a little bit. This first entry becomes -2t over 1 plus t squared. Second entry becomes 1 minus t squared over 1 plus t squared. And I mean, there you go. Okay. And so, like, sort of visually, like, what's going on here is, okay, just like before, we've seen this picture before. The particle is going around the circle very slow and then very quick and then very slow. And the original velocity vector, that's the vector in blue here, that's very short at the left and then very long at the right and then very short at the left again. Well, the unit tangent vector is just that rescaled, so it always has length 1. It's the red vector that just has length 1 all the way around the circle, no matter how quick the particle is moving. Okay, so that's the only difference. It's pointing in the same direction as the velocity vector, but it's always scaled to have length 1. That's what the unit tangent vector is. And the reason we like the unit tangent vector is it gives us a ridiculously nice formula for computing angular speed of a path. Okay, so that's what we're going to do now is we're going to look at how do you actually compute the angular speed of a path. It's not via that definitional formula. It's not via that definitional limit. Okay, how you actually compute it is like this. Okay, so suppose that you've got some path. We're going to need it to be C2, okay? Remember what C2 means is, okay, if you take the derivative twice, you end up with continuous functions. The 2 means second derivative, C means continuous. It has continuous second derivatives, okay? If that happens and the velocity is never 0, then what you do is you compute the unit tangent vector, okay, and then take the derivative of that unit tangent vector and then compute the length of that. And it turns out that equals the angular speed of the path. Okay, so couple notes in order. First off, yes, this is a computational formula, okay? You know how to compute the unit tangent vector. That's what we just did in that previous example. You know how to take the derivative of a vector, right? This is just, you compute like the velocity vector of the unit tangent vector, okay? Great, I know how to do that. Just take the derivative of each entry. And then I know how to compute the length of a vector. You sum the squares of its entries and square root the whole thing. So you know how to compute this beast here, okay? Great, it's a computational formula. Okay, another thing I want to note is that, okay, why do I need C2 here? Like, why do I need second derivatives? And okay, like we're going to do a proof in a moment for like where this formula comes from, and you'll see a little bit of it there. But like sort of already you can see sort of at a high level why I need it, because, well, first I have to compute the velocity vector. I have to compute f prime. For that I need to have first derivatives. And then that lets me compute the unit tangent vector, and then I compute the derivative of that, right? So now I need second derivatives, right? I'm computing the derivative of a thing that was defined in terms of the derivative. So really, I'm taking the derivative of the original function f twice, okay, in this formula here, and therefore I need nice second derivatives for all this to work out. Okay, and also, okay, so again, we're going to prove this in a second, but before we get to that proof, I want to convince you that the formula here at least makes some sort of intuitive sense. Like, why on earth might we even expect that the angular speed, right? Remember, this was the thing involving the angle between velocity vectors. Why on earth might that be measured by this quantity here? And sort of intuitively, what's going on here is that, well, this unit tangent vector, it's a unit vector, right? No matter what time t is, like this little t, no matter what that is, the vector big T, the unit tangent vector, it's going to have length 1. Its length is not changing, okay? So as time goes on, the only component of it that can change is, well, what direction it's facing. Okay, so if you compute the derivative of this unit tangent vector t, this capital T, okay, yeah, like that might be a non-zero thing because like t doesn't have to be a constant vector. It has constant length, but it can still rotate around. It can still change. But the only way it can change is in its direction, in the like sort of angle between two nearby little t values. Okay, so if we measure how big that rate of change is, well, it's kind of just got to be measuring how much the direction or the angle of that velocity vector is changing. And that's exactly what we want to compute, right? That's exactly what this angular speed that we're trying to compute, that's what it does. Okay, so that's just intuition. That's hardly a proof. Let's do an actual proof now. Let's prove this formula here, and then finally we'll close the video with a computational example to see how to use it. Okay, so let's prove this. Okay, let's see where this formula comes from. Let's show that the angular speed, which remember, that's a limit of delta theta over delta t as delta t goes to 0. Let's show that that also equals this quantity here, okay? And the trick that I'm going to do is I'm going to look at this triangle here, okay? So this, I've already seen this triangle earlier. We didn't have this sort of rightmost side on it, but what this is this is one of the unit tangent vectors at some time t, okay? And then this is the unit tangent vector at a slightly later time t plus delta t, okay? I'm saying delta theta, that's the angle between those unit tangent vectors. We had this exact same picture earlier. It was just I said velocity vector back then because we didn't know about unit tangent vectors yet. Okay, and now what we want to do is we want to reason about how quickly this changes as t changes. Okay, and the first thing that I'm going to do is I'm going to use the law of cosines to sort of tell me things about this picture. And in particular, the law of cosines, it tells me that the length of this side over here squared, so delta big T squared, equals, well, the length of that squared plus the length of that squared minus 2 times the lengths times the cosine of this angle here. Okay, so this is law of cosines, and something really nice happens now. And that really nice thing that happens is each of these vector lengths on the right-hand side, every single one of them is just 1, right? Because this is the length of the unit tangent vector at some time. No, unit tangent vector has length 1. Here's the length of the unit tangent vector at some time. No, that's just 1. Length of the unit tangent vector, length of the unit tangent vector, those are all 1. Every single one of these 4 quantities on the right-hand side is just a 1, so that right-hand side simplifies down to a 1 plus a 1, which is 2, minus 2 times thing times cosine, but the thing in the middle is just a 1. So all that you're left with is minus 2 times cosine of the angle in the middle here, okay? So we get this formula here, okay? And all I'm going to do is I'm going to try simplify that and break it down and eventually get it in terms of delta little t. Okay, so the first thing I'm going to do here is, well, I'm going to take the square root of both sides, okay? And if I do that, left-hand side doesn't have the square anymore. Right-hand side has picked up a square root, okay? But now there's a nice trig formula that I can use, okay? The trig formula, or the trig identity, if you remember this trig identity down here, 1/2 of 1 minus cos x equals sine squared x over 2. This is like the double angle identity, okay? Then what happens if you plug that in here, you can get rid of the square root. It's going to cancel with the squared in the trig identity, and you're just left with the length of the rate of change of the unit tangent vector. It just equals 2 times sine delta theta over 2. Okay, very cool. Okay, not good enough yet. Like, sort of what we want to do is we want to get a delta t on bottom, right? Because the definition of the angular speed, it has, it's a rate of change of the angle, or sorry, it's a delta angle divided by delta time. Okay, so we need a delta time on the bottom here. So I'm just going to divide both sides by delta time. And what's going to happen when I do that is, well, I'm going to get the length of delta tangent vector divided by delta time equals, well, the exact same expression that we had on the right-hand side before, divided by delta time. So I've just introduced a delta time on the bottom of both of these. Okay, and now here's the trick, okay? I'm going to try to make what's inside this sign look like what's down here, okay? Or maybe it's better to think about it the other way around. I'm going to try and make what's down here look like the stuff inside the sign, because then I can use facts that I know about limits, okay? There's this very classic limit that you usually see in Calc 1 or Calc 2, where if you have, the limit of sine x over x, where the thing inside, the x, is going to 0, then you have a nice limit. It equals 1. And this is starting to look like that. So I'm going to try to make it look like that. So what I'm going to do is I'm going to say, okay, I've got a 2 in the numerator. why don't I just stick it down in the denominator? That makes this thing down here look a lot more like this thing up here. Okay, and now I gotta go one step farther. Unfortunately, the thing in here, the delta theta, is not the same as delta time. But, well, what I can do is, how about I just multiply by delta theta over delta time, okay? And I mean, I can't really multiply that by that. Like, really what I'm doing here is I'm multiplying by delta theta over delta theta, and then just moving this delta time over to the right, okay? So I'm just sort of introducing an extra delta theta over delta theta, which of course is just 1. It's not actually changing anything here. Okay, and now this is really nice. This is starting to look like something that I can take the limit of because, oh, I kind of recognize that in terms of limits. And like really, like this thing, if I take the limit of that, that's exactly what I want to compute. That's going to be the angular speed. Okay, so now let's throw limits as delta t goes to 0 on this, and we'll just get what we want, okay? So I throw a limit on both sides, and on the left-hand side, when I do a limit as delta t goes to 0, well, that's just the rate of change of the unit tangent vector, okay? That's dt by dt, the derivative of the unit tangent vector. So on the left-hand side, when I throw the limit on, yay, I just get the length of the derivative, which is the quantity in the formula that I'm trying to prove. So that's seeming promising. Okay, what happens now, though, when I slap the limit on the right-hand side here? Okay, well, I get the limit as delta t goes to 0 of all this crap over here. So that's just a copy and paste job so far. Okay, and now what I can do is I've got a limit of a product of two things. And one of my early limit laws that I learned about was whenever I've got a limit of a product, I can split that up into a product of limits as long as the two individual limits in the, like the thing that I'm splitting up in the product of the limits, as long as those exist. So it's okay to do this step here as long as this limit on the left and this limit on the right, as long as those both exist, then everything works out here, okay? And it's just one more line to show that, yeah, those both exist, because, you know, this limit on the left, that's exactly that sine x over x limit that I talked about, okay? This limit here, this just equals 1, and this limit here, this is exactly the definition of the angular speed, okay? So I've just got 1 times angular speed equals angular speed. Hey, I'm happy. Okay, I've done a mild amount of hand waving here, okay? Because here, at this left limit, if you look at this, you'll notice that, okay, it's delta time going to 0, whereas in the limit, I've got delta angle, delta theta. Okay, so how is it obvious that this limit still equals 1? Like, shouldn't it be delta theta over here or delta time in these two slots? And the trick that I'm sort of sweeping under the rug a little bit is that, well, delta theta is going to 0 as delta time goes to 0. If you go back to up to our picture where we sort of introduced delta theta, right? Like as delta time goes to 0, this side of the triangle is moving over towards this other side of the triangle, okay? Like the delta theta, the angle between them, as delta time goes to 0, the delta angle is going to 0 as well, okay? And that's all you need. That's sufficient to be able to conclude that this limit on the left here, this actually equals 1 as well, because really all that matters is this is going to 0, and then the limit of this thing going to 0, well, it's still 1. It doesn't even matter how it's going to 0. It's just as long as it's going to 0 and the thing down here is the same as the thing up here, then yeah, it all works out, okay? So that limit really does equal 1, and it's all okay. Modulo maybe some minor things to make you feel a little bit iffy, but okay. Anyway, great. Formula is more or less proved. Let's do a computational example and then we'll be done, okay? So suppose that you've got positive real numbers a and b, okay? Let's compute the angular speed of the path defined in this way, okay? So a times cos bt and then a times sine bt. Okay, so how do you compute the angular speed of something? Well, what you do is you start with the velocity vector, like we do for lots of these problems, right? So just take the derivative of each of the entries. Cos becomes negative sine, and you get an extra b out in front because of the chain rule, right? In the second entry, sine becomes a cos, and again, you get an extra b out in front because of the chain rule. Great, we've got velocity vector. Next thing, we're going to need the speed, right? We're going to need the length of the velocity vector. Okay, so let's compute that. First entry, squared. Second entry, squared. Square root the whole thing. Use the fact that sine squared plus cos squared equals 1, and it's going to simplify down really nicely like this. The speed is just a times b. And then because now I have those two things, I have the velocity vector and the speed, I divide them, and that will give me the unit tangent vector, okay, what we're calling capital T. Okay, so this is the tangent vector, but just rescaled to have length 1. So it's just velocity vector up here, but divided by AB, and these ABs out in front are just going to go away, and you're just left with negative sine BT cos BT. Okay, so this vector is pointing in the direction of the particle as it moves around the circle, but always has length 1. Okay, next up, how do we compute the angular speed once we've got the unit tangent vector? Well, you just scroll back up to our formula and it's, oh yeah, I take the derivative of each entry with respect to time, and then compute the length of that vector. Okay, so my unit tangent vector, I've got it down here. Compute the derivative of each entry. Okay, well, sine becomes a negative sine becomes a positive cos. Okay, this negative sign just carries down to here, and chain rule kicks in. B gives me an extra B out in front, just like before. And in the second entry, cos becomes negative sine, and I get an extra B out in front because of the chain rule. And now, last step, I've got to compute the length of this derivative of the unit tangent vector. And for that, I mean, same deal as before. It's going to be first entry squared plus second entry squared. Use the fact that cos squared plus sine squared equals 1, and you're going to get, well, just B at the end of the day. Okay, so the angular speed of this path, it's B. Okay, and now I want to talk about this geometrically a little bit. Sort of what's happening here. Like the way to interpret this is the higher the value of B is, the quicker the angle of the particle or the angle of the path, the quicker that's changing. Okay, and it has nothing whatsoever to do with A. So how do we interpret this? Like sort of what's going on here? Well, the parameter A is measuring how big around the circle is. Okay, whereas the parameter B, like this B up here, that's measuring how quickly the particle's moving around that circle of radius A. Okay, so based on what I just said there, that word quickly, if I increase B, then the particle's moving around the circle quicker and quicker and quicker and quicker, so its angle is changing quicker and quicker and quicker and quicker. Okay, what's maybe not so intuitive is that this answer down here, the fact that the angular speed here is B, it doesn't depend at all on A, and that maybe seems a little bit weird at first. The reason it doesn't depend on A, the reason it doesn't depend on the radius, is this particle here, it's going around the circle in, well, 2 pi over B units of time, okay, right? Every time T increases by 2 pi divided by B, it's gone around the circle 1 time, okay? So yes, if you increase A, it's going a farther distance because that radius is increased, it's going around a bigger circle, but the angular change of it isn't changing at all, right? As you change A, it's still just going around 2 pi radians, okay? That's what the angular speed is measuring. It's measuring like this combined change of the angle of the particle, not just literally like the distance that it's traveling, okay? And whether it's a teeny tiny circle or a huge circle, still, like every 2 pi over B units of time, it's just going around 2 pi radians. Like that's the spinning motion of it, basically. All right. That's all I've got for you today. Thanks for watching, everyone. Next time, what we're going to be doing is we're going to be doing basically the same thing, okay? Still, we're going to be saying, okay, here, I've got like a curve or a path or whatever. I want to measure how bendy it is. But we're going to try to take out the component that is how quickly is the particle itself moving. In other words, we're going to try to find something like what we just did today, but that's intrinsic to the curve itself, not the motion of the particle on the curve. Okay, so that's next class, and I'll see you in a couple days for that.